Hello students, in this video lecture we shall discuss the law of large numbers. In previous lectures we have seen that an intuitive way to view the probability of a certain outcome, which is as the frequency with which that outcome occurs in a long run when the experiment is repeated in a large number of times. The probability can be defined mathematically as a value of a distribution function for the random variable representing the experiment. The law of large numbers is a theorem to prove about the mathematical model of probability, and this law shows that the model is consistent with the frequency interpretation of probability. This is also called the law of averages. Before we start the concepts behind this law of large numbers, we should first discuss the Chebyshev inequality based on only simple assumption that the mean is given as mu, but no assumption is given for variance. Let us suppose that a very small positive real number, epsilon, howsoever is small, the probability of the absolute difference that x minus mu is greater than or equal to epsilon should be less than or equal to variance of x upon epsilon square. To prove this theorem, we have a very simple concept that let us suppose that mx denote the distribution function of x, then the probability that x differs from mu by at least epsilon is given by this result. We know that the variance of a random variable x is given by summation over all possible values of x minus mu square mx, and this is clearly at least as large as this summation over x minus mu absolute greater than or equal to epsilon. Since all the summands are positive and we have restricted the range of summation in the second sum, but this last sum is at least, and this is the basically the proof of Chebyshev's inequality, a very fundamental theorem for the law of large number as well as for central limit theorem. Let us start with some law of large number, which says that x1, x2, xn are some independent trial process with finite expected values and finite variances. Here, the concept of variances or the assumption of finite variances is included instead of Chebyshev inequality. Let us the sum Sn is given by x1 plus x2 plus xn. Then for any epsilon greater than or 0, means howsoever is small, the probability that the absolute difference between Sn upon n minus mu is greater than or equal to will tend to 0 whenever n tends to infinite. Equivalently, we can also say that if the probability of Sn upon n minus mu absolute difference is less than 1, then it will tend to 1 as n tends to infinity. We can have the proof of this. Variance of Sn is nothing but n sigma square. Variance of Sn upon n will be sigma square by n, and then expected value is nothing but mu. So by Chebyshev's inequality we can apply this concepts, and thus for fixed alpha the probability Sn upon n minus mu absolute difference is greater than epsilon will tend to 0 as n tends to infinity, or equivalently when probability that Sn minus n minus mu of less than 1 will tend to 1 as n tends to infinity. This is just nothing but the convergence in probability. If this type of convergence is there, that it is tending towards 1 with n is equal to infinity, that is the concept of weak law of large numbers. Let us see the first next slide. Sn upon n is the average of the individual outcomes, and one often calls the law of large numbers or law of averages. The law of large numbers, as we have stated it is often called the weak law of large numbers, whereas in the other case, when this tends to 1 with probability 1, then we say that a strong law of large numbers. This is the basic difference between WLLN and SLLN. Let us consider an example of a Bernoulli trials with the probability P of successes. Let us suppose that xi is equal to 1 if the jth outcome is a success, and It is 0 if it is a failure. Sn will be the sum of the random variable x1, x2, xn is the number of successes and n trials, and mu is nothing but p, that is the mean of each trial. The law of large numbers states that probability that Sn upon n minus p is this absolute difference is less than epsilon tends to 1 as n tends to infinity. The above statement says that in a large number of repetitions of a Bernoulli experiment, we can expect the proportion of times the event will occur to be near p. This shows that our mathematical model of probability agrees with our frequency interpretation of probability. This is the way that how the model is perfect or consistent with the frequency interpretation of probability. Let us see the numerical example. Although Chebyshev inequality proves the law of large number, it is actually a very crude inequality for the probabilities involved in our structure of measure theory or in our probability theory concepts. Its strength lies in the fact that it is true for any random variable at all, and it allows us to prove a very powerful theorem. Let us start with the few examples. Let n is equal to 10 and see the lines drawn for this ranging from 0 to 1. When we increase n is equal to 20, we see have this, then n is equal to 30, n is equal to 40, n is equal to 60, and then for n is equal to 100, you see the picture is just like the normal type of distribution or symmetric distribution. In this section, we shall discuss the law of large numbers for the discrete probability distribution. This law has a natural analog of a continuous probability distribution. We can also go in the next lecture. We shall discuss the examples of continuous probability distribution, that how this law can be interpreted in the definition of frequency. Let us suppose that x1, x2, xn be an independent trial process with a continuous density function. Finite expected value of mu, finite variance is sigma square, and in that situation x1, x2, xn be the sum of xi's. Then for early number epsilon, the limit will tend to 0, or equivalently this is equal to 1. We suppose the proof as it is identical to the proof of the discrete case as we discussed in the previous slides. This theorem is not necessarily true if sigma square is infinite. As in the discrete case, the law of large numbers says that the average value of an independent trial tends to the expected value of value as n tends to infinity, in the precise sense that given a very small number, howsoever small, the probability that the average value and the expected value differ with more than epsilon tends to 0 as n tends to infinity. Now let us discuss again the Chebyshev inequality in the form that there is a there is a random variable with the mean mu, expected value mu, and let epsilon is a be positive real number. Then the proof is complete analogous to the proof of discrete case. We are going to establish for the example of uniform case. Mu is just half. Suppose we choose a random number n numbers from the interval 0 to 1 with the uniform distribution. Then if xi is a discrete I choice, we have mu is equal to 1 by half, sigma square is equal to 1 by 12. Hence expected Sn upon n 1 by 2, variance Sn upon n 1 by 12n, and then for epsilon s, for any epsilon greater than 0, this deviations probability is less than or equal to 1. This says that if we choose a number at random from a uniform distribution 0 to 1, then the chances are better than 1 minus 1 upon 12 n epsilon square, that the difference Sn upon n minus half is less than epsilon. Note that epsilon plays the role of the amount of error we are willing to tolerate. we can this is the our tolerance. This was this. We can illustrate with this large numbers. Says, for example, graphically, the density for an can be determined by this ratio. The law of large numbers tells us that we can and obtain as much as total area as we please inside the shaded region by choosing n large enough, as we have seen this. For the normal case, let us take an example of a normal 0, 1, then mu is equal to 0, variance is equal to 0, then expected value Sn upon n is equal to 0, variance Sn upon n will be 0. And then this probability will always be less than 1 minus n epsilon square. In this case, it is possible to compare the Chebyshев estimate for this in the law of large number with exact values, since we know the density function for Sn upon n exactly. The comparison is given in the following table. Just see the Chebyshev's estimates and the associated probabilities. Now, one more interesting example, we are taking the Cauchy case. Cauchy population is 1 upon pi 1 plus x square. The density function of an is the same for all n. In this case, n increases, the frequency does not change at all, and the law of large number does not hold. Okay, thank you. In our next video, we shall discuss the concept of Lindbergh-Levy theorem and Khinchin's theorem and Kolmogorov theorem.